All right, hello. This video is going to be looking at the frequency response of op amps. And it's a little bit of an esoteric topic, but it comes up in one of the homework problems, so I thought I would go through it in a little bit of detail. So the setup here is you've got an op amp circuit, like the non-inverting amplifier circuit in this picture. And we're feeding it a sine wave. So V in is a sine wave with an amplitude A, frequency omega. And so V out should be just G, the gain, times the input. That's what the theory says. But at some point, and you'll remember doing this in the circuits lab, as you increase the frequency omega, there's a maximum speed that the op amp can keep up with, and it depends somewhat on the gain. And so what we want to know is, for a particular op amp, will it be fast enough for the sine wave? So if you're amplifying things like radio waves or something very high frequency like that, this is an important consideration, and you can get faster op amps, but they cost more money. So we want to estimate, we want to know what is the maximum frequency allowed, and we also, there's some equations for how to predict how badly it will go if you exceed that maximum frequency. So the big number to consider is the corner frequency or the cutoff frequency. This is commonly used in things like filters as well, but it's the highest frequency that the op amp circuit will work. That's the basic idea behind the corner frequency or the cutoff frequency. You'll see the corner in the graph, and cutoff is where it starts to cut things off. So for this circuit here, there's a number that the GBP, the gain bandwidth product, for your particular op amp chip. That number divided by the gain, which is set by your resistors, gives you the corner or cutoff frequency. And if this is in hertz, then it will be in hertz. So for the 741 op amp, which is the one we used all through the circuits lab, a very tried and true old chip, the gain bandwidth product is 1 megahertz, a million hertz. So if your gain is 1, you can go up to a megahertz. If your gain is larger, this gets, the corner frequency gets smaller. That's the main thing. If you are above this corner frequency, the gain rolls off. So that's why this is called the corner, because it's the corner frequency. And the big thing is, if you're trying to operate above this corner frequency, you should probably just go buy a faster op amp. That's the main, that's the best idea. But if you are stuck on a ship and all you have is a drawer full of 741 op amps, you can calculate how badly it's going to look at frequency above the corner frequency. Below the corner frequency, the gain is constant. We assume everything works as predicted. And the summary is, if your frequency on your input is faster than the corner frequency or the cutoff frequency, buy an op amp with a faster corner frequency. If you need to know how bad it's going to be, there are some basic equations. So think of it as a phasor. Since we have a sinusoidal input, the output will be a sinusoid. And the gain, the amplitude is complicated, but the phase shift is really easy. So the phase shift is just negative arctangent of the frequency you're operating at divided by the corner frequency. And so that will give you the shift, which is the lag. There's a minus sign in here because it slows things down. So it will take a little time to respond, and that's shown up as this phase shift angle. The other thing is, you can see as frequencies increase, the gain decreases. And so we approximate this with a straight line when we have log scales, and this is a log scale since it's in decibels. A straight line, and the slope of this line that starts at the baseline gain and corner frequency goes down at -6 decibels per octave. And so the easiest thing is, if you had this graph, you could just see, well, I'm operating at this frequency, and pick the gain off of there. So most of what we're going to do is just how to calculate this change on this graph. So -6 decibels per octave. We know decibel is a way to talk about gain. An octave is the doubling of the frequency. So if you've heard of octaves in music, it also is doubling the frequency. And the oct part is, I think, because of the number of notes. So doubling the frequency is going up by an octave. And so every time you double the frequency, the gain drops by 6 decibels. So you lose 6 decibels. So if we're trying to calculate the gain at a frequency above FC, we have to use this 6 decibels per octave. And we need to know how many octaves we're at. So it's best to see it with some numbers. So here is our non-inverting op-amp, which is where all these equations are based on. We're using the 741 chip with the GBP of 1 megahertz. We're setting up the circuit to be the non-inverting amplifier with a gain of 500. So we picked R1 and R2 so that gain is 500. And then the question is, at 5 kilohertz, if we run a sine wave into this signal into the circuit with 5 kilohertz frequency, what's the gain in the phase shift? Is it above the corner frequency? And if it is, how badly is it off this design, which is a gain of 500 and a phase shift of 0 is what we would like. So the first thing is to calculate the corner frequency based on our gain. So it's 1,000,000 divided by 500. So 2,000 hertz. So yes, we are above the corner frequency, so we're going to have some bad response. So this might be all you need to know, and you go out and you look for a high-speed op-amp in the millions of op-amps that are out there and find one that works fine at 5,000 hertz. But we're going to do the math. So here at 5 kilohertz, we're past the corner frequency. I talked about that. So the gain won't be 500 anymore. It's going to be lower following that chart that we looked at. The phase shift is a one-line calculation. So negative A tan 5,000 divided by 2,000 is negative 68 degrees. So negative 68 degrees of phase shift. If you have like 180 degrees of phase shift, that means you're completely out of phase. So when the input goes up, the output goes down. And that can be really bad for things like feedback control. If you think your airplane is rolling this way, but it's rolling that way, that's bad. So anyway, the phase shift is how lagged the signal is. The gain takes a few more steps. So that's the other thing we want to know. We want to know the gain and the phase shift at 5 kilohertz. So phase shift, super fast. So the gain is based, again, on this graph with the 6 decibels per octave slope. So we need to know how many octaves. So we're at 5,000 hertz, and how many octaves past 2,000 gives us 5,000. So if we were lucky, if it was one doubling, 1 octave would be 4,000 hertz. 2 octaves would double it again, so that would be 8,000 hertz. So we know it's going to be between 1 and 2 octaves, because 5,000 is between these two, so it's good to have a check. And this is the equation we use. 5,000 is our frequency, 2,000 is the corner frequency, times 2 to the n octaves. So when n was 1, we had this, n was 2, have that. So we're solving for the number of octaves here, and it's not going to be an integer this way. So we take the log of both sides and solve for n oct, and we find n oct is this equation. So 1.32 octaves is our answer. That's how many octaves above 2,000 hertz. We find 5,000 hertz. So, and we said between 1 and 2, so that's great. So now we know the gain is reduced by 6 decibels per octave, and we know we're going up 1.32 octave. So the gain is going to be reduced by 7.93 decibels. So we have a gain change of negative 7.93 decibels. So that's the decibels per octave times the octave, and you can balance the units, so that cancels that, and we're left with decibels. Over here on the graph, we can see what we're doing too. We're going over 1.32 octaves, and that's going to bring us down 7.93 decibels on this gain. So we could just read this off. We're starting at a gain of 500, whatever that is in decibels, and we're dropping down this much. So digging in a little bit more, we have two options to say our answer. So we can report the answer in decibels, or we can just use regular gain, the unitless multiplier, and it's your choice. They're interchangeable, and once you get some experience, you don't mind either format. So if we do it in decibels, the original gain is 500, and so we have to convert that to decibels. So we use this equation we've seen before, 20 times the base 10 log of 500. So our original gain is 53.8 decibels. That's shown here on this y-axis. And then we know it's reduced by 7.93 because of the number of octaves we had and the slope of this line. And so we can just subtract them, and we get 46 decibels. So we're down here, and by this math, we're at 46 decibels. So the new gain will be 46. The original design that we were hoping for was 53.8 decibels. There's some round off here, but that's good. So if you don't like decibels, you can convert this change from decibels. So the original gain is 500. That's this 500 is the scale factor. The output is 500 times the input. So a 7.93 decibel, negative 7.93 decibels, is a scale factor of 0.401. So remember, negative decibels means we're reducing it so that the gain is less than 1. And if you plug in 20 times the base 10 log of 0.401, you get negative 7.93. So that's how we solved for this using this equation. You have to invert it with algebra. So we've got the factor, or our scale factor from the unideal response, the factor of 0.401. So at 5 kilohertz, the gain is reduced by that factor from 500 times 0.401 to a gain of 200. So we can say the new gain at 5 kilohertz is either 46 decibels, or we can say 200. Means the same thing, and it's up to you. So that's the final answer. We found the phase shift really quickly, and we find the gain using this graph, these ideas, just extrapolating that line down. So again, if you think of this as phasors, our input voltage was A cosine 2 pi, that's our omega t. And the ideal op-amp with the infinite frequency response, the output would just be 500 the gain times V in, so it would be 500 times V in. But since our frequency is above the corner frequency, we don't follow this ideal equation. It changes. So using the amplitude, the gain, and phase, we can change the amplitude to 200 instead of 500 as predicted, and we have to add the phase shift of negative 68 rather than the ideal phase shift of 0. So that brings it back around to phasors from circuits, if you remember those. And that's the end of this one. So I hope that helps you with the homework problem. We'll be doing a lot more frequency response analysis in filter design coming up in about a week. So this is just dipping your toe in. So it's worth taking the time to understand this kind of frequency response plot where we have frequency on the x-axis and amplitude on the y-axis, and maybe a phase shift graph as well, because we're going to use those a lot when we do filter design.